My name is Jeremy Valance. I'm a research engineer here at Angkor, and I'll be focusing on software supply chain security for cloud native applications. So let's start with a couple of definitions. First and foremost, what is a software supply chain? So a software supply chain is anything that comprises or influences your software from development through your CICD process all the way through to production. And this includes anything that goes into your software development lifecycle, from code to binaries to application configuration. Also includes license information, build metadata, but also includes things outside of that application stack. So anything that you might be using for infrastructure as code or configuration as code, includes who wrote it, who contributed to it, what's the management process for vulnerabilities, anything along those lines. Basically, everything you could want to know about your software and how it was created is exactly what a software supply chain is. Next, software supply chain security. So that's a good definition to describe. Basically, software supply chain security attack is, where there's malicious code that is intentionally added as a component, using the software supply chain as the mechanism to distribute the code. Right? So examples include typo spotting, include malware, basically compromising a CICD platform or a container platform, all primarily or likely with the intent of causing some sort of disruption, whether that's to the software artifact you're building or you're running a software as a service, and there's some sort of downtime or outage to address the attack that's been compromising the software supply chain. And in the context of containers, software supply chain attacks with SolarWinds, it's really trying to spotlight on these supply chain attacks. So we've noticed that just by observing and having conversations with our customers, there's a lot more emphasis on these attacks and really wanting to understand from start to finish exactly what software and dependencies and libraries are going into all of their container image artifacts. Basically, they need to know what's running, how it was built, and that whole kind of concept of this is everything I'm building and everything encapsulated inside of these images. So next, in the context of software containers, we've seen usage rise, right? From 85% of organizations will be running containerized applications in 2025, based on this research from Gartner. And then Synopsys with their open source research saying that open source is pervasive, and that's a good thing. For vast majority of software will be made up of open source libraries. And as long as there's a process in place for managing all that risk, harvesting information about SBOMs and just understanding what needs to happen when a vulnerability needs to be patched, all this usage and increase of open source is certainly a good thing. And next, when we think about containers in general, they have unique properties that allow us to refine our software supply chain. Number one, they're declarative, so all of our dependencies are explicitly described at build time. They're inspectable, so we can statically inspect the contents of the image without having to execute or run that container. We have good insight into this whole image file system that we're looking at that we just built. Third, they're immutable. So once we actually build this container image, it's now content addressable digest, cannot be changed. And then lastly, they're typically short-lived and frequently redeployed. So the process for actually addressing an issue that's impacting a running container is not to actually go into that container that's running and make a change. It's to actually move it back through our CICD workflow with the appropriate fix in place, and then, of course, redeploy. And containers themselves provide us with a very easy way to package and deliver our applications. So we can see in the context of this particular container image right here, where we're looking at the application code, the secrets and credentials, the code artifacts. It's much more than just a list of dependencies and we're done, right? We're dealing with the entire deployment artifact, and there are certain layers within it that potentially are a source of security risks. And risk comes from many different sources. So if we go kind of expand this out, we see that within this application, it's not just our code, it's not just the open source libs that we're pulling in, but we're also dealing with a number of different repositories, right? We have our public repo, other private repositories, individual software vendors, and this is just to really demonstrate for one application. If we expand this out even further, we can see that we start to slowly build out the complexity of the software supply chain greatly. Basically, we have multiple applications now. We're dealing with different public repos, different private repos, and this is really just to illustrate that as things grow, you have multiple applications, you're using many different repos, there's a chain that gets built, and it's really important to understand exactly what the chain looks like, and really try to get a better understanding of all the open source, all of the different pieces of software you might be pulling into your applications and many applications that you're likely running. So how do we address kind of all this risk that we've illustrated? And fundamentally, it's by adopting a philosophy of zero trust, where from the start, we're saying that just because we have all these different stages in my workflow, that does not mean that we should just be able to blindly trust because one passed, the next one's good, and that one was fine. And we have all these vendors upstream that we're just not really paying attention to. From a zero trust perspective, just understanding that there's likely some sort of breach, let's assume it and try to at least engineer or design for methods to address that. And next we can see that for the most part, a lot of DevOps processes and tool chains end up looking like this at a high level. There's some sort of kind of platform layer and then a workload layer. And basically from source to run, we're using a variety of different tooling and instruments to run our containers, to manage our source code, to manage our deployment configuration, to hopefully add the appropriate automated tools and testing within there. And then we can also see if we hit kind of all the security risks that go into this process and tool chain. We have potential for dependency hijacking or kind of compromising of the CICD or package manager, or maybe there's just a zero day that's impacting a container that's running. That's completely plausible as well. And then next, we can also kind of dive a little bit, deeper into some of the other issues that might potentially arise. And one of the ways to address this really is to try to add different layers of security, basically. And if we spread these checks out and hopefully shift as many of them left as possible, we can really try to reduce not only the cost to fix, but the real just overall cost to a breach overall. And this is really kind of fundamentally different from a traditional approach to security, whereas a lot of folks were kind of actually SSHing into a VM and making some sort of changes to that. Now we can hopefully catch all these configuration, whether it's IAC, whether it's CAC, whether it's issues with images, early and often is fundamentally the idea. So what are some best practices we can kind of put into place here? I'll break each of these down in a little bit more detail, but at a high level, it's really establishing a centralized CICD platform and process for all of our software. At no point in time should we really be moving any software into production that doesn't really pass all the gates and checks that we design. Second, build images from trusted sources, right? So any artifact that we're building really shouldn't be arbitrarily pulling information that we don't trust from anywhere on the internet. Thirdly, automate security testing and policy enforcement. So a lot of folks are likely doing some form of this today, but really fine-tuning it and seeing what checks might we have the ability to shift left, what additional policy controls and gates can we incorporate into the system. All these things are really, really important components to add. And then finally, deploying only trusted images into production. So like I said at the very beginning, nothing should ever make its way into a runtime environment. It should be running containers or rogue artifacts in any sort of cluster that we don't know about, that hasn't made its way through this whole end-to-end workflow that we've built. So if we dive into the first one, which is a centralized secure CI/CD process, yeah, definitely use it. Centralized pipelines, all production releases, do as much as you can here to kind of funnel everything through this process. It'll really save a lot of time. And then second here, we can see implement least privilege for each stage. And basically what that means is very rarely are the permissions that you need to check source code in to an SCM are going to be the same to, let's just say, access the cluster of a running container, right? So doing enough evaluation at each stage to say, what are the least privs that this stage needs to actually be effective and accomplish the tasks that need to be done for this particular step in the workflow. Third is, okay, let's take a deeper look at the external systems that we're using. And if we're pulling from some sort of binary repository or artifact repository or container registry, make sure we're trusting these systems in the manner that they should or not. Maybe we don't want any random pulls out from Docker Hub in, and we want to make sure that we're only granting access to a certain container registry. We'll ensure that our CICD platform permissions and whatnot are set up that way. And then finally, document metadata as these images are kind of moving through the stages, right? So if we can add additional bits of information to these container images or to these artifacts that attest that they've made their way safely and effectively through this stage, maybe through some sort of image signing, all that is really important to really secure the CI/CD process. And next, if we jump to building images from trusted sources, we see that this is really all about minimizing the surface area for attack. So using a minimal secure base image with limited dependencies, basically for that container image, nothing really should be unused in that particular microservice, for example. Second is only pull in software that you trust from those approved repos, right? So if you do have a setup kind of binary repo that you're going to allow all your binary artifacts to be pulled from, make sure that that's the only one and we're good there. Third here is write Docker files in accordance with best practice. So there are a lot of good practices out there for avoiding scripting, ensuring the right instructions are present, referencing only the trusted image in your from instruction, no arbitrary curl calls to pull in random packages from the internet. Again, it's really all about minimizing the surface area for attack and understanding exactly what you're building. Your images are going to be that final distribution artifact that you do send out into production. So as small as you can make them to do the minimal set of tasks that they need to do, that's the best way to write your images. And then finally, producing software bills of materials for all of your artifacts, right? So understanding deeply what are all the libraries within them, how can we track vulnerabilities, how can we go back and look at each location for the operating system packages, the non-OS packages inside of this artifact. All that becomes very, very important. So next we can think about, okay, how do we automate all this security testing and all of this analysis, right? So we want to incorporate security checks and quality gates at each stage in your CI/CD. So if you have source code checks like Dependabot for GitHub to look at all your dependencies, if you have just software composition analysis tools that you'd prefer to use, whether you want to scan your container images, which we always promote as a good practice, checking all the container artifacts that support that container image, or really diving in and understanding exactly what objects are going to be created by Kubernetes and what actually ends up running in the cluster. Second piece here is, okay, let's look at this deployment artifact in its entirety, right? We often see a lot of folks kind of just doing a cursory vulnerability scan of the container image, but if we remember back to that anatomy of a container slide, there are a lot of different things that make up this image file system. So it's really important to have a deep understanding of everything that's inside of this file system, not just vulnerabilities, but packages and secrets and kind of everything in between that you'd like to check for. And then storing all that information somewhere so you know this is that kind of container software bill of materials that I have now. Thirdly, track the difference between what you're deploying, right? It's really important to understand, yes, we can look at things in Git to see, okay, these dependencies are changing or these source code bits are changing, but fundamentally, once we build it, we also might want to run an image diff too, just to say, okay, we have this previous version of the image that we created and deployed, and now we're building this, what's actually changing in that file system. And then lastly, from a vulnerability management perspective, it's really important to have a process for not only managing issues and managing new dependencies, but managing when you need to patch, when you need to upgrade a certain dependency. there's going to be a lot of dependencies in a lot of open source, and that's completely fine, as long as there's a workflow in place to say, okay, yes, this is something that needs to be addressed, or no, this is something that we're okay, it's a false positive or what have you. As long as we mark it, we can kind of move forward in this. And then next and finally, it's really all about deploying artifacts that we trust, right? So all deployed images must go through our CICD, right? Really shouldn't be rogue containers. Anything running in the cluster has to really hopefully be signed and then validated that's been signed pre-deployment. Secondly, deploy content, hopefully not using something like the latest tag. You know, sometimes it's good to at least use some type of content addressable digest, so we know exactly this is a unique artifact and that's it, and we can kind of trace it back through provenance when it was built. Thirdly here, validate your application and deployment configuration, right? So we're not just probably deploying a single container image, it's probably made up of multiple different microservices that maybe we're deploying with a Helm chart, and that Helm chart has dependencies, and all those Kubernetes objects end up getting created and deployed and manifested in runtime. And there are security and best practice implications that go into all of those YAML configs. So really understanding exactly what you're deploying. It's likely not just a Docker run. It's usually apply something, and many things get created on the cluster. So, and there's lots of open source tools that can go in and look at YAML config and whatnot. And then finally, enforce policy, both pre and post deploy, right? So if you're using something like admission controllers to validate whether certain pods should have certain labels, or we don't want to deploy this particular type of object, you know, all those things can be really validated right before you actually run that container in cluster, and certainly after that, you can validate where things changing or mutating where they shouldn't be. And that covers kind of the best practices that we had. I can now turn it over to James, and he'll take us through a case study.
Cool. Thank you, Jeremy. I believe I'm good to go now. Let me connect to the slides. Hey, everyone. So my name is James Peterson. I'm one of the Anchor engineers that's been embedded with the DoD, working on a solution to the best DevSecOps platform and securing the supply chain. So now that you understand some of Anchor's capabilities, we can share this customer story with you. So I've actually been working with Platform One, and it's an Air Force organization. And while people typically think of the government as slow and behind the times when it comes to technology, the DoD has been taking a much more proactive approach towards being in the leading edge of the software development as they compete with Russia and China. And so as a result, they're now implementing leading edge DevSecOps practices as part of their software development process. And looks like, Kim, can you advance the slide for me? Thank you. So like I said, one of the major initiatives is called Platform One. It's a complete tool chain for DevSecOps that is architected by the DoD. One aspect of Platform One is Iron Bank, which we'll talk a lot about. It's a repository of hardened containers that is then shared across the DoD as well as other government agencies. Anchor is a mandated tool for use inside this container hardening process for Iron Bank, as well as the DevSecOps reference architecture that was put out there by the Chief Software Officer of the Air Force. So our services organization is also working closely with the DoD, so that it uses the Anchor tool in this hardening process, but also as part of the reference architecture for deployment methodologies for DevSecOps platforms. So first, I want to dive into what is Platform One. Actually, can you go back? Sorry. So this is a quote in the blue, actually directly from their website. Platform One allows users to start solving software problems with an 85% solution instead of starting from nothing. So that's important because Platform One is doing a lot of the heavy lifting for getting an approved modern environment for developing and deploying software. They aim to provide secure and approved base software, secure development environments, and secure deployment environments. So this significantly decreases the amount of time required for the DoD software developers to build their applications and get them into the field for use by warfighters. Next slide, please. Now, Platform One has three main products. All of these are centered around the DevSecOps reference architecture put out there by the Chief Software Officer of the Air Force. First, we're going to start on the right and move left. So first, there's Iron Bank. The output, excuse me, the output of Iron Bank is hardened containers. So these are open source or commercial containers that have gone through the hardening process and been vetted by security engineers and approved by the CSO of the Air Force. Next, we have Big Bang. The output of Big Bang is a push-button implementation of the DevSecOps reference architecture. The intent is to make the architecture easily accessible for anyone to spin up and maintain and immediately be in compliance. And then finally, we have Party Bus, and this is the Platform One SaaS offering, so software as a service of Big Bang. So this is the DevSecOps reference architecture that is run by Platform One, where developers can come and use the approved environment to develop and deploy their applications. They can also use the Party Bus continuous ATO, so continuous authority to operate, to develop and deploy their software with little to no red tape. So let's dig into each product a little bit more. Like I said, Iron Bank is where containers are hardened. More than that, though, the containers are hardened by a team of engineers where they undergo a technical and security analysis. The Iron Bank uses a DevSecOps CI pipeline to automate a lot of the hardening and information gathering for each image. An image will be scanned by security tools, including Anchor, and all of the results are pooled into a centralized database. From here, the data is analyzed by vendors or engineers, and each of the findings from the tools are justified. These justifications are then aggregated and sent to the approving official, the Chief Software Officer of the Air Force, where a final determination is made about whether the container is approved or if it must have some of the findings mitigated, some of the software repaired before it can be approved. On top of initially getting containers approved, though, Iron Bank engineers also maintain the hardened state of the containers so that they're always consumable by anyone who wishes to pull them out of the registry. So how does the Iron Bank implement a DevSecOps pipeline and a secure CI process? Well, we follow a lot of the practices that Jeremy spoke about in the previous slides. Can you skip to the next slide, please? So as you see here, this is just a visual representation of the Iron Bank. So we're taking untrusted software, we're putting it through a DevSecOps pipeline where the software is pulled in, it's built, the container is built, and then it goes through the approval process. And then the Iron Bank is the container repository of trusted software. So next slide, please. So we had one thing that Jeremy spoke about was having a globally configured template. So we have a globally configured pipeline template, and this gives the admins fine-grained control over who can inject code into the pipeline. The admins only have to manage access to the pipeline code repository itself, and all consumers of the pipeline don't have access to change anything and violate the integrity of their pipeline. We also use the lowest permissions necessary for each tool to work with the pipeline. For example, Anchor has a special pipeline user which only has CI access to Anchor, so the bare minimum is needed to accomplish its task. Another important step required for this build pipeline is all of the artifacts are pulled from trusted sources and then saved to the local hard disk before build. Artifacts can then be scanned with an antivirus tool, and then the build can happen disconnected from the internet so that only the trusted artifacts are in the container. And then once all these scans have been accomplished and the analysis is performed, all of the evidence is bundled up and made available for consumers of the container to perform their own analysis. Next slide. So let's dig into how we build images a little bit more, because this is important for beginning to solve the supply chain issue. So first of all, the Iron Bank has an approved base image, the Red Hat Ubi image for now. There's also Scratch and distroless for other containers that might not need a package manager. As I said previously, we do all of our builds fully disconnected from the internet. This means that any scripts run during the build cannot reach out and download potentially sketchy things into our container during build. We also require that the container come with a manifest of all of the dependencies it needs. These dependencies are downloaded in one of the stages of the pipeline before they're sent through a virus scan and then made available to the build stage. On top of building offline from the trusted sources, the Iron Bank pipeline makes use of Anchor Docker file policy to ensure best practices in a secure environment. Things like making sure the container doesn't run as root and enforcing some of the sys benchmarks for containers. The next slide. Finally, the automated analysis of all this data made available during the pipeline. Now, the Iron Bank doesn't have a fully automated system, and that is on purpose because it's providing software to the DoD, and it is a requirement that there be a manual analysis and sign off on these images. The Iron Bank performs its point-in-time scan of a container, and then it provides all of that evidence to an approver. The approver does some manual work up front to perform an analysis on all of the findings inside the container, but then once all the findings have been justified and the process can be fairly automated moving forward, only requiring manual intervention, again, when new findings are discovered inside of the container. Another method of automated analysis comes from the consumers of these Iron Bank containers. So they can consume the Iron Bank containers to build software on top of, and then use something like an Anchor policy to whitelist the findings that have already been justified inside Iron Bank. That way they don't need to repeat the work that Iron Bank has performed. Next slide, please. So up until now, we've talked about the pipeline portion and securing the initial process of creating the software. Well, as you probably noticed, the other products of Platform One, Party Bus and Big Bang, were deployments, and they are where software is actually running in production. Both of these products actually consume Iron Bank images, and Party Bus even provides the hardened images to application developers to build their software on top of. Next slide. So as I said previously, Big Bang is a push button implementation of the DevSecOps reference architecture. Its intent is to provide a repeatable and reproducible environment for software developers to collaborate, develop, and deploy their applications. This allows the environments to achieve a faster authority to operate, which is the approval they require for deploying software inside the DoD. Next slide. So how does Big Bang work with the Iron Bank? Well, Big Bang is an implementation of a Kubernetes cluster with default applications such as GitLab, Mattermost, which is similar to Slack, logging, monitoring, etc. All of these applications in Big Bang have been hardened by the Iron Bank. So Big Bang is deploying trusted images that have been hardened and approved by the Air Force. To enforce the trust over time inside the container, Big Bang uses a custom piece of code called the cluster auditor. It's similar to Anchor's runtime inventory, which is available in our latest product, our latest release. But Big Bang uses this custom piece of code and it inventories all of the images in the cluster and ensures that they're pulled from the Iron Bank. It also provides information about whether the images have been deployed actually have new vulnerabilities inside of them. This ensures full security all the way from the Iron Bank into the running Kubernetes cluster and then through the life cycle of the running software in production. Next slide. Now for Party Bus, Platform One is running the SaaS offering of a Big Bang deployment. Platform One organization has actually received a continuous authority to operate for the Party Bus platform, which allows applications to be developed and deployed and semi-inherit the ATO. Applications developed on Party Bus must still undergo a DevSecOps pipeline, similar to the Iron Bank pipeline, but the cyber team inside Platform One actually evaluates the results and awards an application, what we call a certificate to field, or has them go back and fix any findings that they might find. Next slide. Now, Party Bus consumes Iron Bank images on two levels. One, it consumes the images as part of its deployment. So the Kubernetes cluster that Party Bus is running on actually deploys hardened images out of the Iron Bank. Party Bus, like I said previously, it also offers Iron Bank images to application developers using its tools. The application developers can develop their applications on top of hardened base software, which helps them achieve the approval to deploy in the field. These applications also go through a similar pipeline to the Iron Bank, but they also perform source code analysis on the application itself. This allows not only a secure and trusted environment for the deployment of DoD applications, but it also helps solve many of the issues surrounding supply chain security by giving the application developers the ability to consume secure and approved base software and then develop and deploy in a secure environment. So that's about it for Platform One and the work that Anchor has been doing there. With that, I'll throw it back over to Kim for some Q&A. Thanks.
Thanks, James. Jeremy, if you want to join us back on mic and camera, that would be great. So we have on the control panel a question panel where you guys can answer or enter your questions, and then we'll try to take ones as we go. But I've had a couple that have come in so far. So the first one was about the SBOM, the Software Bill of Materials, trying to understand how that Software Bill of Materials would be or should be used. So Jeremy, maybe that goes to you to at least start with.
Sure. So I'll answer it in the context of, I guess, Anchor or any tool that generates a software bill of materials. So what we first do is try to identify kind of all the packages that may be present in this container image artifact. So we'll go and try to generate a list of all the operating system packages. We'll go also and look for non-operating system packages, so whether it's NPM modules or whether it's Java jars, and really just kind of putting together this list of all of the artifacts that are present inside of this image, the name, the version, and the location within that image. And then we'll store it in Anchor. So Anchor runs as kind of a service that Anchor Enterprise does. Other types of solutions do this as well, where you just basically are now presented with a list and kind of a tree of sorts of everything inside of whatever it is that you scanned. And this is really helpful because when we do actually find out that a vulnerability has been disclosed, it's very easy to kind of track back and say, okay, well, am I actually impacted by this particular CVE? And oh, yes, I am. Let me just quickly query all the artifacts that I ended up having to scan with something like Anchor or something else and see, okay, this particular CVE impacts this package. And I can see that this package is installed in this artifact. And now I can hopefully trace all that back to saying, I have this content addressable digest for this container image that has this vulnerable issue, and it's running here, or it's running there. So generally, that's often how a lot of folks end up, at least from a vulnerability perspective, trying to track back to where everything is running based on this CVE impacts this package and where is that within my environment.
Great, thank you. Okay, so we had a question that I think would go to you, James. It says, when deploying an air-gapped environment, and maybe at the beginning you can explain what that is, would you recommend mirroring the Platform One pipeline to leverage the use of their hardened images, or would you just download the hardened images, save them, and manually transfer them into an air-gapped environment?
Yeah, so an air-gapped environment would be something that's totally disconnected from the internet. So I think both are reasonable, but actually Platform One is aiming to solve this by using a cross-domain solution. So they are actually using Anchor they're using a pipeline to pull images out of the Iron Bank, and then they're using Anchor to scan them along with some antivirus scans, and then putting them through AWS Diode from the low side to the high side where they have disconnected environments. And then in the high side, they use Anchor and antivirus to scan these artifacts again, where they're pushed into a registry, and then they're available to be consumed by clusters on the high side or air-gapped environments. So that, in my opinion, is the most ideal way, because then you don't have to completely copy what Iron Bank is doing, because it is quite a bit of work to actually harden these containers and then achieve the approval and then maintain them. So just consuming Iron Bank and consuming all of that work that Platform One has put into it would probably be my preferred solution.
Great. We had another question come in, maybe for you, Jeremy. Does Anchor scan the packages that are used by the application inside the container, i.e. Java libraries, etc.?
Yes, so Anchor does identify all non-operating system packages, so Java, NPM, Python, Ruby, NuGet. Those are all ones we identify and then categorize as such, and then store in SBOMs and then map to vulnerabilities.
And a follow-up question to that of, does the tool also do source code deep level software license scanning and inclusion into the SBOM?
So we do license scanning for dependencies, right? So if you're doing npm install of something, we'll be able to find the license for that, whether it's available. Yeah.
All right. And then we had another question of whether the, what justifications, can you explain justifications, James? So you had talked about scanning the containers to go into Iron Bank, and then there would be justifications. Explain a little bit about that.
Yeah, so what Iron Bank does is they don't actually remove all of the CVEs or compliance findings out of a container. Some of them, they're there and they maybe don't affect the software, or they don't make sense to be exploited with how the software is deployed. So container hardeners, the section of Iron Bank that actually does the hardening for containers, they will look at, say, the CVE ID, they'll do some research into it, they'll understand how this container, or what this piece of software is doing, and how this CVE applies to this piece of software, and then they'll create what we call a justification. So some bit of text that says, okay, this doesn't apply in this situation because of this reason. And then that is what they pass up to the Chief Software Officer of the Air Force. And then from there, he will review all of those justifications and say, okay, these CVEs inside this container, they're okay to be there because of this background research that has been done to prove that they're not truly as bad as they might seem for this specific container. Now, they might affect other containers or other pieces of software, to the extent that it's reported. But yeah, that's what a justification is. So it's container hardening doesn't actually remove everything. So these containers, they do have known CVEs inside of them, but those have been accepted risk for the containers.
So that kind of goes to the next question. Maybe you've addressed it a little bit, but it said, what would you recommend to do for OS and non-OS vulnerability findings that do not have a fix?
So right now, it depends on how bad that finding is. I mean, if it's a critical, then there's going to have to be, especially in the Iron Bank, there's going to have to be some sort of workaround in the software to not use that finding, or to not use that afflicted piece of software. If there's something like a low or negligible, again, it goes back to the justification, whether that is acceptable, and what kind of attack, what kind of data is this exposing for this piece of software.
And then a question about, for James, working closely with Platform One, he asked if there's any updates to having a Stig Ubuntu image. And maybe you can explain what a Stig image is as well for the non-federal folks here.
Yeah. So a Stig is a secure technical implementation guide, I believe is what it's called. But it's basically a set of rules to say, this is a secure piece of software. It's mainly been applied at like runtime for a computer, if you will. So stigging for containers is relatively new. Platform One has attempted to solve that solution. So we actually use a tool called OpenSCAP, which I believe is from Red Hat, and we'll spin it up inside of a container and we'll run a Stig profile on it. So it will perform a series of checks in a container and basically pass or fail that container on whether it has this Stig runtime environment. But as far as an Ubuntu container, that is being worked right now, but it's not currently available in Iron Bank. I'm not sure on the exact timeline, but it is actually being considered.
And then a question for you, Jeremy. Does Anchor monitor the container engine, usually the Docker engine, for malicious account activity?
No, not currently. We don't have any hooks into the container infrastructure or the Docker daemon. We've had kind of discussions later on about roadmap on what things we might like to add to kind of bring us a little bit closer to other pieces of the kind of container stack and runtime. So we're definitely exploring all those options that we have.
All right, well, thank you everybody for attending. We appreciate it. Look out in your email for a link to the video for review or to share with others on your team. If you want to click this link or visit our website, you can always schedule a demo with us or get some additional information about our solutions. Thanks everybody. Thanks, James. Thanks, Jeremy.